This is one of the best videos on atomic orbitals and hybridization of atomic orbitals available on the net, and it will surely blow away your mind. First, imagine an atom as a small house with special rooms where electrons live. Electrons in atoms are not tiny balls spinning around the nucleus like planets around the sun, which we have been used to imagining from old textbook pictures. In reality, as per quantum physics, they behave more like guests moving around inside a room, rather than marbles circling a center. You can't point to one exact spot and say that the electron is right there, because it keeps shifting around within its space. Instead, you can only say that an electron is most likely somewhere inside this particular room. That whole room where the electron can move freely is what we call an orbital. Some rooms are round like a bubble called s orbitals, and some are shaped like peanuts or p orbitals. But in every case, the electron moves within that space rather than following a fixed circular path. Orbitals have different shapes because electrons behave like waves, not tiny balls. These waves must fit around the nucleus in specific patterns where their energy is stable, just like a vibrating drum or guitar string can only produce certain shapes of vibration. You can think of this like musical notes on a guitar string. The simplest note, when you pluck the string gently, vibrates evenly and gives a smooth sound that is like the s orbital. But if you press the string of a guitar in the middle, it forms two halves vibrating opposite to each other. That's like a p orbital, with a node in the center. The node is the point, or a plane, where the wave amplitude is zero, meaning the electron wave never exists there. The more complex the vibration, the more complex the shape of the orbital. Now, each set of rooms belongs to a particular floor of the house. This floor number is what we call the n state, or principal energy level. The first floor, or n equals 1, is closest to the center and holds only one round s room, while higher floors, or n equals 2, or n equals 3, and so on, have more rooms, like one s room and 3 p rooms for n equals 2, and sometimes even d or f rooms on higher levels. Also note that these orbitals are not flat or 2D shapes drawn on paper. They are three-dimensional spaces in which electrons move. The s orbital is perfectly spherical. Then the p orbitals, on the other hand, have two lobed shapes, like dumbbells or peanuts, and come in three types, one along the x direction, one along the y, and one along the z together, giving the atom reach in all three dimensions of space. Okay, this is how we can represent the energy levels or floors and orbitals or rooms using this simple 2D representation. But remember, as mentioned, that actual orbitals will be 3D like this. Each room can hold a certain number of electrons, just like each bedroom can only fit so many people comfortably, right? Now, the electrons that stay on the outermost floor, that is, the highest n level, are called valence electrons. These are the ones that decide how the atom behaves when making friends or forming bonds, because they are the easiest to reach and share. The number of these outer electrons determines the atom's valency, or how many bonds it can form. For example, carbon has 4 valence electrons, so it can make 4 bonds. Keep that in mind. Now, when an atom wants to form bonds, that is, make friends with other atoms, it may find that these orbitals are not arranged in the best possible directions. So, to make better connections, the atom remodels its orbitals by mixing them. This process of mixing orbitals to form new ones is called hybridization. It's not like the atom consciously chooses to do it. Hybridization is really our way of explaining what happens inside the atom as it prepares to bond, so that the final structure and bond strengths make sense. Before bonding, each atom has orbitals s and p with fixed shapes and energies. But when another atom comes close and bonding is about to happen, the atom's electrons feel the presence of this approaching partner. At that moment, the energies of its s and p orbitals adjust, and it becomes more favorable, energy-wise, for the atom to mix these orbitals into new ones that can point exactly toward the incoming atom. These hybrid orbitals exist only when bonding is about to occur, or while the atom is bonded, not in the free isolated atom. That's why, for example, a free carbon atom doesn't have hybrid orbitals. But when carbon starts forming bonds, like in methane, ethene, or ethane gases, its s and p orbitals mix into sp3, sp2, or sp hybrids, depending on how many bonds it's forming. Let us talk about hybridization of carbon atoms. Carbon has an atomic number of 6, meaning a neutral atom has 6 electrons to place into its atomic rooms, or orbitals. We always start with the lowest energy room and fill upward. This is known as the Aufbau principle. The very first energy level, called n equals 1, has only one round spherical room, or the 1s orbital. This room can hold a maximum of 2 electrons, so we place the first 2 of carbon's 6 electrons here, filling it completely. Next, we move to the second energy level, called n equals 2. This energy level has one s and one p orbital labeled as 2s and 2p. The 2s room is next in energy, and it also fills up with the third and fourth electrons, leaving 2 more electrons to be placed. These final 2 electrons go into the 2p subshell. Basically, px, py, and pz are the 3 subshells of p orbital. Now, according to the Hund's rule, which is a rule that electrons prefer in order to take separate, empty rooms before pairing up, the remaining 2 electrons will occupy 2 different p rooms, each with 1 electron and parallel spins. This is a very important detail because it leaves the atom with 2 unpaired electrons ready for bonding in its most stable state. The complete electron configuration of carbon in this ground state is therefore read as 1s2, 2s2, and 2p2. The last 4 of these valence electrons are used to form the backbone of all life, which is why carbon is so incredibly versatile. Okay, now let us first understand sp hybridization. When we say an atom has sp hybrid orbitals, we mean one s orbital and one subshell of the p orbital, which can be one of the px, py, or pz that have been mixed together. This mixing produces 2 new identical hybrid orbitals, and we call them the 2 sp orbitals. They always point in exactly opposite directions, making a straight line, or 180 degrees, apart like this. So, for example, if the atom mixes its s and px orbitals, you get 2 sp hybrids along the x-axis, one in the positive x direction, one in the negative x direction. That's what happens in molecules like acetylene, the gas used in welding torches. For carbon to form the triple bond as seen in acetylene, it needs to get 4 unpaired electrons ready for bonding. It does this in 2 steps. The first thing that happens is that one of the paired electrons from the 2s orbital jumps up to the empty 2pz subshell. This creates the excited state, which is 1s22s1 and 2p3. Now the atom has 4 unpaired electrons. The carbon atom preparing for sp bonding only needs 2 hybrid rooms pointing in opposite directions. Therefore, it takes one of the s orbital and one px subshell and mixes these 2 rooms together to produce 2 identical opposite hybrid rooms, which we call sp hybrids. This way, as you can see here, we have this carbon atom that has 2 sp hybrid orbitals, which corresponds to this carbon atom, and then we have this carbon atom that has 2 sp hybrid orbitals, which corresponds to this carbon atom. Now, hydrogen has 1 valence electron, and it has 1 s orbital. So, this carbon atom makes head-on, or what we call sigma bond, with this hydrogen atom. Similarly, this carbon atom also makes a sigma bond with this hydrogen atom, and completes its electron pair. Now these two carbons also bond in a straight line along the x-axis, forming one sigma bond. So, a sigma bond is formed when two hybrid orbitals meet head-on along the line joining the two atoms, like a direct handshake. Now, after forming two sp hybrid orbitals, each carbon still has two leftover p orbitals that are not used in hybridization. These unhybridized p orbitals, or py and pz, form sideways overlaps called pi bonds. Py of this carbon form pi bond with this one, and pz of this carbon form pi bond with the pz of this one. So a pi bond is formed when two unhybridized p orbitals overlap sideways. But this sideways overlap happens only after the sigma bond is already in place. So, in acetylene, between the two carbons, one sigma bond and two pi bonds make a triple bond. That's why triple bonds are strong and have shorter bond length, as they have both head-on and sideways connections holding the atoms tightly together. Now, if this is clear, then understanding sp2 and sp3 will be a piece of cake. For sp2 hybridization, let's take one s orbital and two p orbitals. When they mix, they form three identical sp2 orbitals. Each lobe looks like sp only, but these orbitals spread out evenly in one flat plane, like three spokes of a wheel or three arms of a fan lying flat like this. The angle between any two of them is 120 degrees. A good example is ethylene, the gas used for making plastics. In ethylene, each carbon forms three sigma bonds using its sp2 orbitals, two with hydrogen atoms like this, and one with the other carbon. The remaining unhybridized p subshell, say pz, on both carbons overlap sideways to form a pi bond. That's why ethylene has a double bond between the two carbons, one sigma and one pi bond. Now, because the pi bond locks the two carbons in one plane, the molecule cannot easily twist. This is why double-bonded compounds are usually flat and rigid. Great. Now finally consider the sp3 hybridization. Here, we will mix one s orbital with all three p subshells. The atom now forms four identical sp3 orbitals. The shape it forms is called a tetrahedron, which is like a triangular pyramid, and it looks like this. This arrangement minimizes electron repulsion and results in a bond angle of approximately 109.5 degrees between the bonds, which helps the molecule stay perfectly balanced. A great example of sp3 hybridization is methane, which is the main component of natural gas. The carbon atom in methane uses four sp3 orbitals to form four strong sigma bonds with four hydrogen atoms. Because all four orbitals are equivalent, the bonds have equal strength and are of equal length. So, hybridization is just a smart model chemists use to explain why molecules have the shapes they do. Making these kinds of videos takes a lot of time, research, and effort, so I'd really appreciate it if you could like, share, and spread this video as much as possible. Your support and feedback give a lot of motivation to keep creating more such helpful lessons. So